Hello, and welcome to this biomechanics video about joint load analysis. What I mean by joint load analysis is where we think about the loads that are being applied externally to the person, so say from standing, and we think about what those loads translate to at some joint of interest, so maybe the forces that creates in the knee, or in the hip, or in the spine. To do this, we're going to apply the standard engineering principles that you learned in statics and dynamics. But first, we need to talk about some basic assumptions that we're going to make about the human body. So, when we think about the human body, we have bones for our purposes, we have joints, we have muscles, and tendons, which we're going to consider together, even though they're different. We'll talk about why in a minute. And we have ligaments. So, assumptions here. Bones. We're going to assume that bones are rigid. That's not valid structurally, but it's an assumption we're going to make for this analysis. We'll see when we talk about bone mechanics that bones actually bend and deflect. Joints. We're going to assume that joints have kinematic constraints. So kinematic constraints you learned about in statics and dynamics. So that's things like a joint might be rigid. That's an example of a constraint. Or a joint might be a simple ball and socket joint. So an example of a ball and socket joint, simple ball and socket joint model is the hip. An example of a rigid joint would be the pubic symphysis. Okay. So, or a joint can be more complex. So examples of that, and this I should be clear here is an example. Examples of that include the knee or the shoulder or the wrist, where there's a combination of motions going on. So the knee is not just a simple hinge. That would be a simple model of the knee. The knee actually, in addition to bending and rotating about this point, the knee actually slides back and forth. And so if you want to model the knee more fully, you need to include all of those degrees of freedom. The most important thing about your joint model is that you match your model to the question that you're asking. And that is number one, the most important thing about any model and any assumptions that you make. And the validity of your results, the usefulness of your results, very much depend on how your model matches the question that you're asking. Muscle and tendon, we're going to consider functionally together because they work together to transmit force, even though they're actually different, molecularly different tissues. So we're going to consider them functionally together, and we're going to assume that they act along a straight line. Now, there's a lot of work in biomechanics where you think about how the modeling or how you model muscle and how you think about its generating of force, and we'll talk about that in muscle mechanics. But for right now, we're going to assume that muscles and tendons work together and that they act along a straight line. They generate force in that direction. And that direction is in a line from the origin to the insertion of the muscle. Finally, ligaments, again, are gonna act along their line from the origin to the insertion, same as that. But their purpose is to carry load across a joint. So they carry load across a joint. So these are our assumptions for our models when we start to talk about using statics and dynamics to apply to the human body. Now, for statics and dynamics themselves, let's start out by thinking about statics. Statics, as you recall, is this idea that the sum of the forces is equal to 0 because the acceleration is equal to 0, and the sum of the moments is equal to 0. Whoops, the sum of the moments, the moment is the vector, not the sum, is equal to 0 because the rotational acceleration, alpha, is equal to 0. So that's statics. The benefits of this method is that it's easy to do. A equals 0 is nice. It's easy to work with. The con here, the major flaw in this, is that when we're talking about movement or interesting situations, in interesting situations, A is rarely 0. So when we think about the body moving, when we think about it getting injured, almost always A is not 0. So it provides some information, but it's limited information if we make a statics assumption. Now, we often do this in biomechanics, where we'll make something we call a quasi-static assumption, which is basically just saying that A is equal to 0, even though we know it's not. So a quasi-static assumption, A equals 0, even though it doesn't. And that's both A's, alpha and A. So you can do this. It limits the usefulness of your conclusions. So the pros are that it's a useful first approximation. And if you read the fine print on the Hutchinson Dinosaur T-Rex article, you'll notice that they make that assumption in that article. The cons are that it's not realistic. And then there's dynamic analysis. Dynamic analysis is the same as the force analysis. Oh, I did it again. Some of the forces. Except here we remember that really we're talking about the sum of the forces is equal to mass times acceleration, and the sum of the moments is equal to I, the mass moment of inertia, times alpha, the angular acceleration. So this is more complicated on a couple of levels. One, you have to know alpha and A. And two, you have to know the mass moment of inertia. You calculated the mass moment of inertia in statics and dynamics, and possibly also in mechanics of materials. And, there were some things like this for a rectangle, and you could go look those up in the table. Well, you can make assumptions that the human body is made out of things like trapezoid shapes that you could look up in a table, but if you look at your own body, it's probably not so much. A tapering cone might be more realistic for your arm or something like that. So figuring out what I is makes dynamics more complicated, in addition to needing to know A and alpha. So the pros here are that this is more accurate, assuming that you can make accurate assumptions. The con is that it's much, much harder. It's more difficult and more computationally intensive. So that means you need more computer power in order to solve the problems. Fundamentally here, though, the most important thing to remember is that the assumptions that you make in solving a problem define the usefulness of your solution. The assumptions that you make define the usefulness of your solution. So if you make an assumption about how the knee moves that does not involve sliding, but you're asking a question that requires sliding at the knee in order to answer it, your results will be garbage. So it's important to match your model with your assumptions, or with your question. Okay, we're going to take a look at some examples, but this gives you an idea of where we're going to get started.